In our previous lectures, we have discussed Einstein's field theory, field equation of general relativity in very detail. We have seen what is Einstein's field equations, in fact, in the presence of matter and also in empty space. And you also know whenever there is a field equation, definitely there is a need to solve that very equation. So what will be the solution of Einstein's field equation? This was a vital problem. And actually, to solve this problem, so many mathematicians were working, but the first solution of Einstein's field equation, particularly in empty space, was provided by a well-known mathematician, Schwarzschild. And in this lecture, our aim is to discuss the Schwarzschild solution of Einstein's field equation particularly in empty space. Okay? So you can also say that we are going to discuss Schwarzschild's exterior solution for the gravitational field of an isolated particle. Okay? So definitely we will have to start from Einstein's field equation, particularly in empty space, and then we will see how Schwarzschild provided its solution. Okay? This is a very important lecture particularly for your examination purpose. Okay? You know, Einstein's field equation in empty space, you have learned in my previous video that this is given by the Ricci tensor R mu nu is equal to 0. This is Ricci curvature tensor. Okay? When you say that R mu nu is equal to 0, it means you are saying that the space-time is flat. Actually, in empty space, the space-time will be flat. So, keeping this very idea in mind, Schwarzschild provided the exterior solution for the gravitational field of an isolated particle. Okay? So this equation, which reads as R mu nu, that is the Ricci curvature tensor equal to 0, you know, this is Einstein's field equation in empty space. Actually, while writing this equation, you would know that we have neglected the cosmological constant. But in derivation of Einstein's field equation, Einstein himself has considered a constant which is called cosmological constant. So if you will consider the cosmological constant denoted by this symbol capital lambda, then this field equation, which has been written in equation 1, becomes like this. This is R mu nu is equal to lambda times G mu nu. Okay? Here this capital lambda, you know, this is called cosmological constant, which is actually a very small quantity. So in practice, we more or less neglect it. Okay? Now our aim is to solve this equation 1, or you can say 2. When you say we are going to seek the solution of equation 1 or 2, what actually that means? Actually, the solution of these equations merely consists of finding the line element or the metric for interval in empty space surrounding a gravitational point particle, which ultimately corresponds to the field of an isolated particle continually at rest at the origin. Okay? So this solution, as I have told you, was first of all provided by Schwarzschild, a well-known mathematician. Okay? So when we are going to seek the solution of this Einstein field equation, it means we are going to see what will be the metric or what will be the line element when we consider that there is a gravitating particle, there is a point mass, which is responsible for which is responsible for the gravitational field. But in the vicinity of that very particle, there is no other mass. There is no other gravitating medium. Okay. So we simply say that that very particle is isolated, and this solution is also called Schwarzschild's exterior solution for the gravitational field of an isolated particle. Okay. Now what will be the metric or the line element, particularly in a spherical polar coordinate system, in the absence of any point mass. What will be that metric, or what will be that line element? In the absence of any point mass, the space-time definitely should be flat. And so, the line element in a spherical polar coordinate system must be like this. This is ds square equal to minus dr square minus r square d theta square minus r square sin square theta d phi square plus dt square. Actually here we have taken c equal to 1 in natural unit or in gravitational unit, Okay. If you will not take the natural unit, then here in last term you have to write c square dt square, but for convenience we use either the natural unit or the gravitational unit, where we take c equal to 1. Okay. Actually, this line element or the metric which has been defined in equation 3, this represents the space-time. This represents the flat space-time in absence of any gravitating particle. Okay. But the presence of the point mass will definitely modify the line element. If you consider that there is a point mass present in that region, then this line element will get definitely modified. However, since mass is static and isolated, the line element would be especially spherically symmetric about the point mass, and also it will be static. Okay. So the most general form of such a line element may be expressed like this. This is ds square equal to minus e to the power lambda dr square minus r square d theta square minus r square sin square theta d phi square plus e to the power nu dt square. Actually here this lambda and nu, this in first term I have written e to the power lambda, and last term e to the power nu. Actually these lambda and nu are functions of r only. It means lambda is a function of r and nu is also only a function of r. Okay? Since why it should be only the function of r? Because for a spherically symmetric isolated particle, the field will depend only on r, and that's why we say that these numbers lambda and nu must be a function of r only. They do not depend on the other two coordinates theta and phi. Okay. Now, since the gravitational field, particularly in absence of any gravitating material, when you say gravitational field, what does it mean? Gravitational field is nothing. This is simply the disturbance from flat space-time. In absence of gravitational field or in absence of any gravitating mass, the space-time is flat. But when there will be there will be a source of gravitation, the space-time does not remain flat, it becomes curved. So due to a perturbation, a flat space-time becomes curved. Okay, and there, so that I am saying that gravitational field is what? This is disturbance from the flat space time due to a particle. Okay, and this gravitational field, decreases and decreases, diminishes indefinitely as we go to an infinite distance. From a gravitating point mass, if you will move to infinite distance, there will be no effect of gravitation there. So the gravitational effect or gravitational field reduces to zero as r tends to infinity. Okay. So in this condition, when r will tend to infinity, in this limiting condition, these numbers lambda and nu must tend to zero. And when lambda and nu will be zero, you can see e to the power lambda, that is e to the power 0 will be 1, e to the power nu, that is e to the power 0 will be 1, and this line element defined in equation 4 will be just as defined in equation 3. That is, this will just become the space time of this will just become as the line element or metric of a flat space time. Or you can also say that it reduces to Galilean space time defined in this equation 3. Okay? But this will happen when r tends to infinity. Okay? Now, you have studied earlier in my course provided on tensor analysis that the line element in general relativity is given by this expression, or the matrix is given by this expression ds square equal to g mu nu times dx mu dx. Okay? Here the four coordinates, if you are talking particularly a spherical polar coordinate system, then x1 means r, x2 means theta, x3 means phi, and x4 means t. Okay? Now we will compare equation 4 and 5 with the help of this equation 6. In fact, in equation 6 we have recognized x1, x2, x3 and x4 as r, theta, phi and t. So when you will keep the notion of this equation 6 in your mind and you will compare equation 4 here with this equation 5, then the fundamental tensor or the matrix tensor G mu ni is given by this matrix. This is a 4 by 4 matrix defined here. You can see. You can easily see that only the diagonal elements or diagonal components of this matrix tensor are non-zero. The first diagonal element is minus e to the power lambda, second is minus r square, third is minus r square sin square theta, and fourth one is e to the power lambda. You can easily see. These are actually the coefficient of dr square, minus e to the power lambda, and for d theta square this is minus r square, for d phi square this is minus r square sin square theta, and for dt square this is e to the power nu. And all the off diagonal elements of this matrix are 0. Now if you define this matrix tensor G mu nu by this matrix, then you know what will be the determinant of this matrix tensor. Actually the determinant of this G mu nu denoted by this symbol small g equal to determinant of G mu nu, you know what will be that? That will be simply equal to the product of these diagonal elements, because all the off diagonal elements are 0. So determinant of G mu nu is simply equal to product of the 4 diagonal elements, and hence This determinant is given by product of minus e to the power lambda times minus r square times minus r square sin square theta times e to the power. And so this is simply minus e to the power lambda plus nu times r4 times sin square theta. Okay. Now, if you have calculated the determinant of this covariant fundamental tensor, then you can easily find the contravariant fundamental tensor. And you have earlier studied in your course on tensor analysis that this contravariant fundamental tensor G mu nu, this is defined as cofactor of G mu nu in determinant of G mu nu, that is G, and divided by determinant of G mu nu. And therefore, you can see the expression for this G mu nu here, and its determinant is defined here. When you will divide this G mu cofactor of G mu nu by this determinant, then you will get the contravariant fundamental tensor, and that is given here. You can do it. This is here. You can also see that all the off diagonal elements of this matrix are 0, and only the diagonal elements are non-zero, and these diagonal elements are what? These are minus e to the power minus lambda, minus 1 over r square, minus 1 over r square sin square theta, and e to the power minus 2. Okay. Now, using the idea of Christoffel symbols, you can now obtain the solution of Einstein's field equation in empty space, which was actually provided by Schwarzschild. On that manner, we will follow the process. And for this, if you consider that mu, nu, sigma are different indices, then with no summation convention, you have earlier studied in detail the Christoffel symbols. In this condition, you know this Christoffel symbol gamma, mu, 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 this will be given by 1 over 2 g mu mu times del g mu mu by del x. And this can be, you can check, this can be written as 1 over 2 del log of g mu mu by del x. When you simplify this del log g mu mu by del x mu, you will get this much. Okay. And gamma nu mu nu, this is defined like this. These are all just the definitions, and you have studied it earlier. And gamma nu mu nu, this will be defined like this. And again, this product g nu nu times del g nu nu by del x mu can be written as partial derivative of log of g nu nu with respect to x. And gamma mu sigma gamma sigma mu nu, mu sigma, that will be equal to 0. Okay. Now, using this formula, you can easily obtain the 9 independent, non-zero or non-vanishing 3 index symbols, and all others are actually 0. So using these results, you can see easily that this gamma 1 1 1 is equal to 1 over 2 del lambda by del r, gamma 2 1 2 is equal to 1 over r, gamma 3 1 3 is 1 over r, gamma 4 1 4 is 1 over 2 del nu by del r, gamma 3 2 3 is equal to cot theta. Okay. Gamma 1 to 2 is equal to minus r e to the power minus lambda. Okay, so in this way we can obtain all these values. Okay, now after obtaining these values, you can see how we can find the solution or the line element for Einstein's field equation in empty space. You know, Einstein's field equation in empty space, we have seen this is r mu nu is equal to 0. So now our aim is to obtain this r mu nu. Okay? And you have learned earlier, you have studied Ricci tensor. I have provided a separate video on it, that this Ricci curvature tensor r mu nu is defined by this expression. This is partial derivative of this Christoffel symbol with respect to x nu minus partial derivative of this Christoffel symbol with respect to x beta, and the two quadratic terms. This is just the basic definition. Okay? But now you can see this gamma beta mu beta. You have seen that actually this is gamma, this mu mu mu. This is equal to this much. So utilizing that result, now you can easily see that instead of this gamma beta mu beta, we can write this much. This is actually del log square root of determinant of g by del x mu. And when this operator will be operated, you will get the second order partial derivative of log of square root of determinant of g and with respect to x mu and x nu. Okay? This term has been, this term is at ease, you can see, and this term is also at ease. And again in last term, instead of this Christoffel symbol, I have written this. Okay? Now writing the expression for this r mu nu, now you can obtain the different components of this r mu nu. First of all, we are going to find the value of r11. It means mu is 1 and nu is also 1. This can be easily obtained. Simply we will replace mu and nu in this equation 11 by 1. So when you will replace mu and nu by 1, your result will be like this. Nothing has been done. Simply mu and nu has been replaced by 1. You can see. Okay? Now, now as we have seen that x1 is equal to r. Okay? x1 is equal to r. So in first term there will be del r, this will be del r square, and therefore expression for r11 becomes like this. This is second order partial derivative of log of square root of determinant of g del r square minus del r, this Christoffel symbol, plus the product of these two Christoffel symbols, plus this much, plus this much, plus this much, minus this much. Okay? But you have seen earlier that the determinant of g is equal to this much, and therefore the square root of determinant of this g will be equal to e to the power lambda plus nu over 2 times r square sin theta. Now we will substitute this value of a square root of this fundamental tensor in this result here. And when you will substitute this value of determinant of g in the expression for r11, this will become r11 equal to del 2 by del r square, this much, minus del r 1 over 2 del lambda by del r, plus 1 over 2 del lambda by del r whole square, plus 1 over r square, plus 1 over r whole square, plus 1 over 2 del nu by del r square minus 1 over 2 del lambda by del r times del r operated on this. You can check it. Okay. And now when you will simplify it, your result will be 1 over 2 del 2 nu by del r square plus 1 over 4 del nu by del r whole square minus 1 over 4 del lambda by del r times del nu by del r minus 1 over r del lambda by del r. Okay. So in this way we have obtained the first element of r mu nu, this is r1. Actually in the similar manner now you can obtain r22, r33, r44. Okay. You can easily find. I have written directly the results for these without any calculation. So for your examination purpose you must remember these. R22, this will be e to the power minus lambda times this much and minus 1. Okay. R33, this is e to the power minus lambda times this much minus 1 times sine square theta. So you can easily see that the expression inside this square bracket is nothing, this is simply R22. Therefore, instead of this expression inside the square bracket, you may write R22. So R33 is equal to R22 times sine square theta. Okay. And R44, this is given by minus 1 over 2 e to the power nu minus lambda times this much. Okay. You have seen earlier that for this line element, all the off diagonal elements of r mu nu are identically 0. Okay. So these are the diagonal elements r11, r22, r33 and r44. These are non-zero and all of diagonal elements are 0. But when you will see that after obtaining this, we will think about the Einstein's field equation in empty space. You know, Einstein's field equation in empty space are r mu nu equal to 0. And when you talk r mu nu, it means it will have actually 16 components, among which only the diagonal components are from r11 to r44 are non-zero and all other are 0. So when we will set the value of r11, r22 and r33, then the Einstein's field equation for different components of this Ricci curvature tensor will become like this. This is r11, which is equal to 1 over 2 del 2 nu by del r square plus 1 over 4 del nu by del r whole square minus 1 over 4 del lambda by del r times del nu by del r minus 1 over r del lambda by del r, that will be equal to 0. And similarly r22, which we have defined here, this is also equal to 0. And r33, which is simply r22 sine square theta. So r33 will be equal to r22 sine square theta, and that will be equal to 0. But sine square theta is not 0, so you can say that r22 is equal to 0. So you can see that equation 13 and 14 are not different. Equation 14 is same as that of equation 13. Okay? These are not independent, but they are completely same equation. And this is the expression for r44, and now we will set it equal to 0 while writing the Einstein's field equation. So r44 is equal to this much, and that is equal to 0. Okay? And as I have told you that equation 14 is not a different equation. This is simply the mere repetition of equation 13. Okay? So we have now 3 Einstein's field equation in this condition for r11, r22 and r44. r22 and r33 are same. Okay? Now for getting the line element, in this condition, we will have to do some algebra. And for this, first of all, we will divide this equation 15 by the factor e to the power nu minus lambda, which is present here. So when you will divide this equation 15 by e to the power nu minus lambda, in RHS, you can see in RHS this factor will cancel out, okay, and the remaining terms will be this much, 1 over 2 times this much, and then this result will be subtracted from equation number 12, okay. So when we will subtract that resulting equation from equation 12, you will see your result will be 1 over r del nu by del r plus 1 over r del lambda by del r, and that will be equal to 0. Now 1 over r can be taken as a common factor, and so your result will be del nu by del r plus del lambda by del r equal to 0. Now when you will integrate it, d nu by dr times dr plus d lambda by dr times dr, and this will be integral of 0 dr. Then this will be simply nu, this is lambda, and this will be 0 plus some integration constant. So after integration, we obtain nu plus lambda equal to a, where you see that a is a constant of integration. A is what? This is constant of integration. Now this constant of integration which have come in our calculation, this can be set equal to 0 without the loss of any generality. Why we can take it 0 and there will be no loss of generality? Because you know, when r tends to infinity, then both nu and lambda become 0. So if we will take a equal to 0, our result will be not affected. So the simplest value of this constant which we will set, that will be equal to 0. So now let us set a equal to 0. After setting a equal to 0, our result is nu plus lambda equal to 0. It means lambda is equal to minus nu. Lambda equal to minus nu. Now this value of lambda, which is equal to minus nu, we will substitute in equation number 13. Equation number 13, that is in the expression for R2. Okay? See this expression, and we will take lambda equal to minus nu. Okay? So in this factor e to the power minus lambda, this will become e to the power nu. This term and this term will become same with opposite sign, and therefore you can see when we will use this result lambda equal to minus nu in that very equation, our equation will be e to the power nu times this much minus 1 equal to 0. Now sum of these two terms will be r times del nu by del r, okay? And that is equal to 0. Now this expression, that is e lambda plus r times del nu by del r, this can be written as del r times e to the power nu. You can check it when you will actually differentiate it, you will get this result. Now after integration, you can see the integral of r times e to the power nu is equal to integral of dr, and therefore this will be simply integral of differential of r to the power nu is equal to integral of differential of r. and this integral will be r e to the power nu, and this is r plus b, where b is another integration constant, and therefore e to the power nu will be equal to r plus b divided by r, and that is equal to 1 plus b by r. Now this constant b is taken equal to minus 2m. We set it minus 2m. Why it is taken minus 2m? Actually here m is mass of the gravitating object. In fact, this is done in order to facilitate the physical interpretation of m as mass of the gravitating particle. Okay? So if we recognize the constant b equal to minus 2m, then the line element which you have defined in equation number 4, you can see in equation 4, what is your equation 4? You can easily see. Sorry, the page has been turned, but this will be just okay, don't worry. When I work with this iPad for a longer time, sorry. Okay, not taken. So this is then that equation 4, which I am not turning the page, that will become minus 1 minus 2m over r whole to the power minus 1 times dr square minus r square d theta square minus this much, and here 1 minus 2m over r dt square. Okay. So this solution was first of all obtained by Schwarzschild, as I have told you, and hence it is known as Schwarzschild line element or Schwarzschild matrix. Now you can easily see that when we take the limit r tends to infinity, then this factor 2m over r will be 0. This will be 0. And therefore, the expression for ds square in this limiting condition will become like this. This is the expression. But you can see this expression for line element is for flat space, or you can say the Euclidean space. So I have written here that this is actually the line element or matrix for the flat space-time of special relativity. So this result, which is called Schwarzschild line element or Schwarzschild matrix, this was obtained by Schwarzschild for the solving the Einstein's field equation in empty space. Okay. So I think you have clearly understand the idea behind this solution, and this, as I have told you, that this Schwarzschild solution of Einstein field equation for empty space is very important for your exam purpose. So go through the video seriously, watch it seriously, and write down these things in your notebook, revise it. Everything will be clear. Okay, thank you very much.